All right, the last joint, let me get a share screen going. The last joint is the configurable joint. This is all of the other joints rolled into one, plus more. My guess is that all of the other joints are based on this configurable joint, just wrappers around it. It provides for restrictions and accelerations on motion, rotation. Targets can be orientations or angles. There are more properties than you can shake a stick at. Uh, here's a little example showing you the length of the configurable joint uh, set of uh, options. There are just tons of them. Some of it is similar to the character joint in that we have uh, the we of course have connected and anchor. Those are standard with any joint. The object to which the joint is connected, and the anchor, which is the point to which the effects apply. We also have dominant and secondary axes, sort of like the twist in swing 1 and swing 2 of the character joint. But there's a lot more. Um, with we have settings for the X, Y, and Z motion, and these can be either locked, in which case they don't move, or they can be limited, in which case we use the linear limits below, or it can be free to move. And we have the same set of choices for the angular X motion, the angular Y motion, and the angular Z motion. These are rotations about X, Y, and Z axes. The linear limits are all done the same way. They have a limit that is a plus or minus range. Uh, they have a bounciness, how it behaves when it hits the limits. They have a spring that will draw them back to the zero and a damper that will damp out the spring oscillations. For the dominant axis, we have high and low angular limits. And for the angular Y and angular Z, we have secondary axis constraints of this same form. We have target positions. We have target velocities. So we want it to be moving at a certain speed, or we want it to be placed in a certain position. And we have various drives that will move it to those target positions or velocities. We have a position spring if we're moving to a position, and we have a position damper if we're moving to a position. We also have the maximum force that will be used to achieve a velocity. Uh, uh, we have target rotations. We'll talk about quaternions later. This is another way of expressing the Euler angles that set the rotation of our object. We have target angular velocities, how fast we want it to spin. We have various drive modes, X and Y, Z, sometimes called swing and twist, or slurp, which is spherical linear interpolation. And we have various X and XZ drives, lots of different choices here. Um, um, then the protection and distance and protection angle, these are the same as we've seen before. We can also configure in world space, in which case we ignore all these axes and we use world coordinates. And of course, they all have a brake force and torque. Now that all sounds pretty daunting, but let me show you a fairly simple example, a prismatic joint. And this is one that only slides along one axis and has some limits, like a drawer or a sliding door. So we make a cube, add a rigid body, some nominal mass, add a configurable joint, and then leaving everything alone, we set the Z motion to limited and the others, all others, to locked. We set the linear limit to 1, the spring to 500, and the damper to 0.5. And so this is what I have here, the slider that has X, Y locked, Z limited, and angular all locked. The linear spring limit is 500, the damper is 0.5, and the linear limit is 1. Everything else I've left at default, and so I don't even have to look at them. And so here's my prismatic joint. It has a target position here, and if I'm using my drag to move it around, if I drag it back over here, it gets stuck for some reason, it closes. So we have a sliding door or drawer. Another example is to fix one of the problems that we had with the blob shadows. If you remember with the blob shadows, don't save, I'll save. With the blob shadow, we had this projector that projected down on the object, and the problem was, if we watch this thing while it plays, the problem is that as the thing rolls, the shadow ends up pointing different directions, and so the shadow ends up not being down underneath it, but it rotates. And we can fix this so that now we're using a configurable joint, and with this, if we watch this one, now the projector stays quite nicely above our rotating object, and it continues to cast its shadow below it, unlike the old blob shadow that is rolling around. So again, this is the configurable joint, but it's not that difficult to set up. Well, we make an empty game object for the root. So this time, instead of the ball being the basic object, in this case, an empty game object with a rigid body and a configurable joint is the object. We're going to add to that a child that's just one of our ordinary blob shadow projectors with the usual settings, mesh renderer. I've got a trail renderer just for fun, and also as a child of that object, the sphere, the thing that I want to cast the shadow through. The configurable joint has only one setting. We're setting the X, Y, and Z motions to all be locked, and we're setting the X, Y, and Z angular motion to all be free. Everything else we just leave alone at the default settings. So X, Y, and Z are locked, and angular X, Y, and Z are free. The only settings that I changed. And this makes now a blob shadow projector that doesn't care if the object below it is rotating, and that's a good thing. So I'm going to stop sharing there. This has been a long haul through the physics of Unity, but I think you're seeing that these are very powerful tools. So I'll stop sharing. I'll end the recording, and I'll see you all in class. Bye.